Okay, I'm not sure if anyone's logged in yet. I'm going to give it about 2 more minutes before I go ahead and start with the lecture today. If you are watching in the live chat right now, can you just pop into the live chat on the side and let me know that you're there? I would appreciate that. Okay, we are going to go ahead and get started. So today we're going to be covering Chapter 3, Landscapes Fashioned by Water. Ignore the fact that it says Fall 2015 at the top. I apparently failed to update my slides. Okay. So first, just a couple focus questions. What are external processes and what role do they play on the rock cycle? So an external process is a process that occurs at or near the Earth's surface. So it's a process that is not instigated within the Earth. It is something that's happening to the Earth. External processes are powered by energy from the sun, and they are what transform rock into sediment. So remember last week we talked about weathering process, break down rocks into smaller pieces, which are called sediment. And then that sediment is typically redeposited and formed into a rock. So external process can include weathering, the decomposition and disintegration of a rock like we talked about. Mass wasting, this is where you have rock and soil being transferred downslope under the influence of gravity, such as a landslide or a rockfall. And then erosion, which is the actual physical removal of material by a mobile agent, usually water, also glaciers or ice, and then wind can be a physical mover. And we're going to talk about these three in relation to the Earth's surface on a large scale rather than the small scale of individual rocks. Okay. There we go. So mass wasting, like we said, is the downslope movement of rock and soil due to gravity. So there are 4 general types of mass wasting. You have a slump, you are a debris slump, you have a debris slide, you have a rock fall, and you have a mud flow. Okay. So physical and chemical weathering are what set the stage for mass wasting. Mass wasting usually occurs after a slope has been weakened due to weathering events on that slope. And what happens then is these mass wasting events are usually large-scale events that transfer debris downslope and then change the slope profile over time. So you can see the original slope here is a very steep-sided slope. Well, once you have a slump occur, and it's a much more gradual, gentler slope down. Mass wasting events are not always predictable. There are a number of calculations that scientists are able to use to try and determine if a mass wasting event is likely, but it's impossible to accurately predict when and where a mass wasting event will occur. So controls and triggers of mass wasting events. So why do these happen? The biggest trigger of a mass wasting event is water. So if you're in an area that all of a sudden gets a very large influx of water, that water reduces the internal resistance and adds weight. So if you have water being introduced into a soil unit, it keeps those grains of soil or grains of sediment from attracting to one another, and basically it lubricates the grains so that they are more likely to move. Additionally, this water is filling the void space between the sediment grains that was originally filled with air. And water is much heavier, much more dense than air. So all of a sudden you have the same volume of material that is much, much heavier because you've just put water into all of that void space. Additionally, you can get an oversteepening of slopes. When you have an oversteepening of a slope, you can get increased erosion because it is the potential energy for those sediments to be moved down slope is much, much higher. It's a lot easier to move something down a very steep slope than a very gradual slope. And the removal of vegetation can increase erosion. Roots hold soil and sediments together. That's why heavily forested areas tend to have very well-developed soils, whereas steep slopes with very little vegetation or no vegetation, especially out west, we tend to see a lot more of these mass wasting events because there is not enough there to hold these soils together even with the introduction of water. Additionally, earthquakes can trigger a mass wasting event. Earthquakes introduce vibrations to the sediments, and these vibrations will actually cause these sediments to lose their attraction between one another and shake them loose and then move that material downslope also. So it reduces the internal resistance like water without adding any additional weight to the slope. We started to talk about the water cycle in your introduction. Okay, so just a brief review of the hydrologic cycle. This is when water moves between the ocean, the atmosphere, and land. It's a summary of the circulation of Earth's water supply. So it is a very generalized picture of how water moves within the Earth systems. Processes in the water cycle include precipitation, or rain or snow, evaporation, filtration, runoff, and transpiration. Okay, we will cover each of these. So here's just a very simple image of the water cycle. So here we start with the precipitation of the snow or rain onto the mountain. I guess it would be snow, because then we have snow accumulating, and it proceeds to melt and run off to the surface. Once that water reaches the surface, we get overland flow, typically in the form of creeks or rivers. That's our surface runoff. Eventually, it accumulates in a basin, such as a lake or a pond, or even the ocean systems. So if you have an accumulation in a lake or a pond, you do have a layer of ground beneath it. So this subsurface allows the water to actually slowly infiltrate from that lake into the ground. You get a groundwater system. So when people talk about groundwater, there's actually water that is contained within the rock and the sediment beneath the surface. It moves at a very slow pace, but it does move. Then you get uptake from plants. They pull moisture out of the soil and into their branches and leaves. Plants actually then expel moisture. They actually give off water through their development. That's transpiration. You can also get evaporation of surface water. As that water moves into the atmosphere, it then condenses to form clouds, which are then transported and precipitated out, and the cycle begins all over. Okay, you will need to be able to identify the hydrologic cycle for your exams, so I would suggest that you kind of just get associated with the basics of this. So the hydrologic cycle is powered by the sun. So when water enters the atmosphere, it enters through evaporation. So when water particles are heated up, they change phase from water to vapor, and that vapor is less dense in the atmosphere around it, and it rises. The wind then transports that water through the atmosphere, where it precipitates either on the ocean or continents. Precipitation to the ocean completes the hydrologic cycle. It's just that, two-step cycle. But if it precipitates on the continent, it needs to follow a path back to the ocean. So some water soaks into the ground. That's infiltration. When a soil reaches its saturation point, so it cannot take any more water in, the surplus water, the additional water, then flows over the surface in runoff. Water absorbed by plants is eventually released by transpiration, like we talked about. Now, transpiration and evaporation are very hard to quantify, so they're typically combined into a single effect called evapotranspiration, which is a general catch-all for what we think is movement in the water cycle based on these two effects. And then precipitation in colder regions actually become a part of glaciers, which are significant long-term reservoirs in the hydrologic cycle. So we talked about the surface water or runoff. So surface runoff eventually becomes channeled into streams. These streams intersect each other and get larger until they converge into rivers. River systems are comprised of many, many streams and creeks, and all that surrounding land area of those streams and creeks that contribute to a single river is called a drainage basin. Drainage basins are separated by what we call divides. So a divide is when you have a drainage basin, such as the Yellowstone River Drainage Basin. Along the perimeters here, you'll have what's called a divide. This is where if a drop of water fell right here on this line, it could either drain into the Yellowstone River Basin or it could drain into the Missouri River Basin. So it could either go to the right or go to the left. It's usually a high point. So most drainage basin divides are ridges, and it's basically a splitting area where you can either go down one hill slope or down another. So focus question here is, in which watershed is Jamestown located? Okay, so that one should be a pretty easy one for those of you who are actually located in Jamestown. It is in the Chautauqua Lake watershed, which is in the larger system of the Lake Erie watershed. So here's a better picture of a divide. So you can see you have your valleys here, and then you have your ridges. Drop of water falls on this ridge, it can either go to the left or to the right. So your drainage basin is everything that would drain down towards this valley right here and out. So here's some local watersheds and divides. So Jamestown is right in here, and it is in the Greater Great Lakes watershed. Okay, so I apologize. Lake Erie does not have a separate one. It is the generalized Great Lakes watershed. Okay, there are 4 distinct drainage patterns associated with surface runoff. So a drainage pattern is the pattern of the networks of streams in an area. The common patterns are dendritic. These are streams that form on areas of uniform bedrock, so all the bedrock underlying this is basically the same. And it makes this kind of like tree formation, okay, where all these little streams coming in into bigger streams until the biggest stream is like the trunk of your tree. You can get radial. This is a pattern where it basically originates from one single point, and these are typically associated with volcanoes or isolated mountains or domes. You can have your rectangular. If you get a highly jointed bedrock, so a bedrock that breaks evenly in regular intervals, you can get these rectangular, very 90-degree angle kind of stream patterns. And finally, a trellis pattern. This is very common in areas of alternating weak and resistant or weather-hardened rock. So you have ridges of very weathering resistant, and then valleys of rock that's easily weathered. So you get defined channels in the areas that are easily weathered, and then streams coming down from the ridges of the less weathered ridges, giving you these very defined single orientation with smaller streams coming in at about 90-degree angles. So this is looking at the Jamestown area geomorphology, because we have to understand the landscape to better understand the actual drainage area here. So if you look at the legend here, the higher the elevation, the redder it gets. Lower elevations are blue, higher elevations are red. So here we've got some green, and then these yellows then would be areas of higher elevation until we get to our peaks. So these reds here are peaks within our elevation, and these valleys. So Lake Chautauqua is actually in a low point, which makes sense, right? That's where you would get a lake developing. And this is a better image of, so the Lake Chautauqua, and then some of the drainage patterns in these other regions with all the streams coming in. So what kind of drainage pattern would best fit the Jamestown area? Okay, so if we look closely at these, the best example is probably not Lake Chautauqua. It's probably over here towards the east a bit. We've got a lot of channels coming in at different angles contributing, so we're probably looking at a dendritic. The Chautauqua area is a lot of glacial deposits that are fairly uniform. Okay, once we define a drainage system, we need to actually talk about the river system because river systems aren't uniform their entire path. So a river system involves the stream network contributing to it, the drainage basin it's located in, and then the river development downstream. So it can be broken into three sections. You've got your zone of sediment production, so your areas of high erosion. These are your steep regions, your very mountainous high slope angles. Your zone of transportation, which is an area of moderate slope, very wide flat plains. And then your area of sediment deposition. This is a very low-lying, very flat area, typically along the coastline or along the edge of a large water body. Okay, water flows in two ways. It can flow in laminar flow, which is where water basically moves in straight lines that are parallel to the channel. So if you had a river channel and you just drew lines straight through it, that's what it would look like. Or turbulent flow. This is where water moves erratically in a swirling fashion. So when you get the very active water you see in creeks at high flows, where it looks like it's moving in different directions almost, this is your turbulent flow. So your very straight laminar flow, and then your turbulent flow. So when we talk about the stream flow, the ability of a stream to erode or transport material is determined by its velocity or by its speed. Okay, so streams can have a significant impact on the rocks and the landscape around them. But to understand how much of an impact they have, we need to understand their velocity. So factors that determine the velocity is the gradient or the slope. Higher slopes have higher speeds. Like if you were on your bike and you went down a very steep mountain slope, you'd probably gain a lot more speed than if you were on a flat plane and you took control off, you'd probably just kind of fall over. Channel characteristics can affect it. So the shape of a channel, if it's very curvy, it's going to slow you down. The size of a channel and the roughness. If you have a very smooth underlying channel bed, it's going to move a lot easier than if you had a really bumpy, rocky channel bed. And discharge. The volume of water can actually have an impact on velocity. Okay. When we talk about streams, you'll hear the phrase a stream profile a lot. This is the cross-sectional view of a stream. Okay, this is viewed from the source or the head of a stream to the mouth or the end of the stream, like that picture we looked at here. So this would be a laminar view, or I'm sorry, a longitudinal view where we're looking at the head of the stream all the way down to the end of the stream. A profile is a smooth curve that shows how gradient and velocity decrease downstream. Factors that increase downstream, okay, so gradient and velocity decrease downstream, but discharge and channel size increase downstream. So here's a longitudinal profile of California's King River. So you can see at the head, your elevation, you have much higher slopes, okay, because you're traveling a short distance but having a huge change in elevation. Right about here, you probably move into the sediment transport range. You can see how the slope becomes much more gentle, less steep. And then as you reach probably the sediment deposit region, it becomes almost flat because you're barely changing in elevation as it reaches its output here. So when we talk about the stream head or areas of erosion, we have higher velocities in these areas because of the gradient, right? So sediment in these areas can be moved by either abrasion or dissolution. So the stream moves loosely consolidated particles. So what we mean by this is particles that are still, like if you scooped up a handful you could, shake it all out. It's not yet formed into a rock or any sort of really cohesive material. So the stronger the current, the more effective it is at lifting particles. So this is the Hillstrom curve. This is in your textbook. This really gives a quantification of the velocity needed to begin eroding particles off of a channel bed. So you can see here that you would need a very high velocity to erode small clay particles. Once you reach the silt, it starts to become a little easier. Once you reach sand, we go from needing velocities of about 800 centimeters a second. We're in the medium grain sand, we're only needing about 50 centimeters per second of velocity to move them. As we start to get bigger, though, it starts to require more and more velocity. So why does it take more energy to cause clay to erode than sand? Because smaller particles mean they're easier to move, right? So here's the thing. If you look, it says cohesive clay and silt. So what happens is that clay and silt is a bit packed together, and clays tend to be charged particles. So they attract more strongly to one another than a sand would. So because they're so much more cohesive, it actually takes a lot of force in the water to break those bonds between the clay particles. Whereas sand doesn't have that attraction between particles, and it's very, very easy to start instigating movement. Here we're looking at the transition zone. This is the zone where you wouldn't be eroding the material, you might be just kind of scooting it down the path. And for clays all the way through sands, a velocity of 20 centimeters a second or less, you're not going to get any movement. You're actually going to get deposition of sediments. That is just too slow to move anything. Okay, you do need to look at this image. I really want you to study it because this is an extremely important concept when examining how rocks are eroded and how that sediment is moved. Okay, if you have any questions about this, please do not hesitate to ask me. I cannot stress enough how much you need to understand this image. Okay. So when we talk about transporting sediment, the material that's being transported is called the stream load. Okay, you have your suspended load and your solution load and your bed load. Okay, solution load is also dissolved load. So a dissolved load is when you actually get the ions from chemical weathering carried in solution. So if we have a limestone and the calcite is weathered out, those calcium carbonate particles are now dissolved in the water and carried in solution. A suspended load is the physical transport of particles within the water column. They don't touch the bottom of the stream bed at all. They are fully distributed within the water. And finally, bed load are gravel, pebbles, and larger rock that are too heavy to be picked up and transported in the water. Instead, they are moved along the stream bottom by rolling, sliding, or what's called saltation, or basically hopping along. Streams also have a capacity. This is the maximum load a stream can transport. So streams can only carry so much sediment at a time. And then competence, which is the maximum particle size a stream can transport, determined by velocity. So this table here gives us what the competence of a stream would be. If we can measure the velocity, then we can tell you what the competence would be. I'm going to have you guys watch this video on your own. Again, YouTube is always kind of crummy. So I really want you to think about this, though, when you're watching the video. What happens to the boulders when the stream profile flattens out further downstream? Base level and stream erosion. Base level is the lowest point to which a stream can erode. There are two types of base level. There is the ultimate, or sea level. Basically, a stream can never erode below sea level because that is basically it's the lowest continental point on the planet. Everything discharges into the ocean. If you erode down below sea level, it actually starts to accumulate sediment until it builds back up to or above sea level and discharges down again. So you will never be below sea level. Another is a local or temporary base level. These are usually caused by geologic events or human impacts, such as building a dam, which could change the lowest level your stream will erode. Changing conditions can cause readjustment. So raising the base level or making that base level higher would cause deposition of sediment, and lowering the base level would cause erosion. So deposition of stream sediment is caused by a decrease in velocity. When you decrease velocity, like we saw in that table, competence is reduced, so it cannot carry as much sediment. So that sediment that it can no longer support because of the grain size begins to fall out. Stream deposits are typically well sorted. Okay, what this means is that the heaviest particles always fall out first. So you always have, in an area that used to carry water that no longer does, you'll get the largest particles on the bottom and the smallest particles up on the top. Now these stream deposits are called alluvium. So this takes a look at how adjusting the base level changes the conditions. So here's our original stream profile. So this is, our nice curve for our longitudinal, a little steeper here, a little flatter here. Now we've put a dam in here. What we've done is we've artificially raised our base level on the stream. So our base level used to be way down here. Well, now we have a base level where the elevation is up here. So because of this, our streams start to deposit sediment in here to accommodate our new base level, and we build up a reservoir with excessive stream deposits around its perimeter. Additionally, lowering of regional base levels can be caused by uplift of the earth or drop in sea level. So if you have a volcanic activity that is quickly increasing the elevation of your Earth's surface, that can impact it, or if you have a drop in sea level for some reason. Raising of the base level can be caused by a subsidence of Earth or a rise in sea level. So there's been a gradual rise in sea level, which is causing a bit of a change in base levels. But the most common is the subsidence of Earth, or erosion of especially cliff sides that very quickly change the elevation of a region. Streams can be broken into two different types of stream channels. You have your bedrock channel, which is where a stream is actively cutting into solid rock, and then your alluvial channel, which is made of unconsolidated sediment. The most common stream type are the alluvial channels. Those are the ones you'll typically see around Jamestown. They're flowing through unconsolidated sediment, lots of rocks, lots of gravel. Furthermore, alluvial channels can be broken into two more types, meandering and braided. A meandering channel keeps most of its load in suspension, so most of the sediment is carried within the water column. They meander or they move in very deep, smooth channels. Okay, so it usually looks like a single section or snake of water. And meandering channels tend to have a slightly lower velocity, so they mostly move silt and clay. They don't have enough velocity to move sand and gravel. Meanders, because of the velocities within the stream channel, erode on the outside of a meander, so out here, and deposit on the inside. So they erode on the outside or the cut bank, and they deposit on the inside, or what are called point bars. This is a good video to watch of meanders and how it will erode on the outside and deposit on the inside. Please watch this on your own. This is just showing you some cross sections of a meandering channel. So this shows if you have a straight section of stream, your highest velocity is going to be in the top center of your stream. Okay, because of the friction between the water and the stream bed around the edges, you're going to have your lowest velocities here. Well, once you start to encounter a curve with the outer edge here, because of the movement of this center of the stream, you actually start to get your faster velocities migrating towards the outside of that curve there. Faster velocities means it's able to move larger pieces of sediment and more sediment, causing erosion on this outer edge. Okay, next section is shaping stream valleys. Stream valleys are channels and surrounding terrain that contribute to water. Valleys are shaped by weathering, overland flow, and mass wasting. So when we talk about stream valleys, we're basically describing smaller regions within a drainage basin. There are two general types of stream valleys, your narrow and your wide. Your narrow are V-shaped valley deepening valleys. They are comprised of a headwater that downcut toward the base level, and they often feature rapids and waterfalls within them. Valley widening are areas that occur at base levels, so they have basically eroded down to the lowest elevation possible. So you have very less downward erosion, and stream energy is directed, instead of focusing the energy on eroding down, it is directed from side to side, creating those meanders. Okay, so this is looking at how you shape a stream valley over time. Streams almost always start out as a narrow V-shaped valley. You get these very high defined ridges. As these streams start to erode, they lower the elevation of that. I'm sorry, that's super loud. They lower the elevation of that region. They erode away material until you get a much gentler slope. And as they do that, they start to focus their energy on side to side. As they do that, they start to widen their stream valley. Okay, so you went from a very narrow one to a much wider one here, until it gets to the point where it's extremely widened and you develop a well-developed floodplain. These floodplains are where a lot of agriculture starts to occur, because floodplains are very high in nutrients, very flat, easy to farm regions. Okay, moving on to depositional landforms. The most common depositional landform is a delta. This is a body of sediment where a stream enters a lake or an ocean. And these result in the sudden decrease in velocity. So if you have a stream moving at 5 meters a second and it hits the ocean, that ocean's not moving that fast. That ocean is moving at significantly slower speeds because it's not going anywhere in the broadest sense. So what happens is, all of a sudden, you have that stop in movement, and so that water has no velocity. It can't support the sediment within it anymore, and it just drops it all straight out. Another depositional landform are what are called natural levees. These form parallel to the stream due to flooding that occur over many years. So as the water floods, as it first goes over that stream bank, it deposits its coarsest sediment right there, and where you have the initial velocity drop. And as you go further out, the water starts to lose more and more velocity, depositing finer sediment. This builds up a small natural levee, and as this occurs over multiple flood events, you start to build up higher and higher natural levees. Finally, like I alluded to earlier, we have our floodplains. So these are these regions in a channel or a stream valley that are flat, low-lying portions that are subject to periodic flooding. Because they're so flat, any flooding that would overbank these natural levees would easily flood this entire valley, because there's no change in elevation. It's all the same elevation here. Some additional floodplain features, for instance, one is a cutoff. So what happens is a meander migrates downstream and slows due to resistant material, and an upstream meander catches up and erodes the narrow neck. So what happens is you start to get this very sharp bend in your meander with a very small neck here, and the stream, essentially, I'm like anthropomorphizing your stream here, but your stream basically decides it's easier to just jump over this little section of earth here and erode it away than to go all the way around this curve, because that takes a lot of energy for water to move through that curve. When this jump happens, it cuts off that former meander and creates what are called oxbow lakes. These are just abandoned bends in the meander, and they typically turn into wetland or marsh regions for a while. Okay. Back swamps are floodplains where fine sediment settles after a flood, and these are usually located far behind a stream's natural levee. So here is the natural levee or buildup along a stream bank, and the back swamp is just where all that clays and muds get deposited. Floods are the most common and destructive geologic hazard on Earth. Floods can be natural or human-induced, and heavy rains, rapid snowmelt, failure of human-made dams, and topography and surface conditions can all contribute to flood events. This is a flood event that occurred in 2009 in western New York. I was not actually in New York for this. Someone told me about it, but apparently it was pretty damaging to a lot of areas. So check this video out. This is a video of some catastrophic flooding in the Sichuan province in China. You will see entire skyscrapers taken out in this video. The power behind these flood events is just mind-blowing. So now that we've covered that happy topic, moving on to groundwater. Okay, there we go. Groundwater is the largest freshwater reservoir for humans. That's where most of our water source comes from. In the geologic roles, groundwater acts as an erosional agent and dissolves, creating sinkholes and caverns. It's also an equalizer of stream flow. This just shows you the distribution of freshwater between groundwater, ice sheets, and lakes. So groundwater is actually the largest portion of water currently available for human consumption. Very good. Oh. Okay, the distribution of groundwater. So you have your belt of soil moisture. That's the top portion of the soil, and that water typically infiltrates through to reach the groundwater system. You have your zone of aeration. This is an unsaturated zone where pore space is mainly filled with air. Then you have your zone of saturation where all pore space is filled with groundwater. When we talk about the water table, we're talking about the upper limit of the zone of saturation. So right at that boundary between the zone of aeration and the zone of saturation. Go deep enough in certain areas, so be over 500 feet, and you can actually get groundwater that is salty. This is because of many of the salts, the halites, or even the calcium carbonates that are contained within the groundwater. So this just shows you a cross-section of groundwater. So typically, especially in our area, streams actually intersect the groundwater system. This is the elevation of your groundwater. So as you go upstream, you can see you would have to go further and further down to reach the groundwater bed. We have an aquitard here, which is a very impermeable layer of soil, so typically like a clay. And what happens then is water that's infiltrated down actually gets stuck on top of this. That's where we get our seeps or springs that come out of the side of a hill. It's because they're perched on a clay layer, and so they come out to the surface and then continue on overland flow. And this is just showing a well that was drilled into an aquitard and was able to reach a waterbed. Groundwater movement is it's similar to surface water, but it is dependent on a few more variables. Groundwater is dependent on the porosity of your soil or rock. Your porosity is the volume of pore space in that unit. This determines how much groundwater can actually be stored in that soil. Permeability is the ability to move water between those pores. Okay? Porosity and permeability are not the same thing. Porosity is the empty space in your soil. Permeability is the connectivity between your empty spaces. An aquitard is an impermeable layer that doesn't readily transmit water, and an aquifer is a permeable layer that does transmit water. When we talk about springs, you can get hot springs, which is where water that is warmer than air occurs, and this is typically heated by the cooling of igneous rocks. So as igneous rocks start to cool and form, they output that heat, and that heat is actually migrated through the groundwater system, creating hot springs. Geysers are intermittent hot springs where water turns into steam and erupts. So here's a picture of Old Faithful erupting. If any of you have not made it out to Yellowstone National Park, you should go. It's really awesome and mind-blowing. Moving on. Some of you may have heard the term artesian wells. This is where water in a well rises higher than groundwater level. These act as natural pipelines moving water from areas of recharge to the point of discharge. So what happens is, if you look here, we have interbedded areas of pervious or permeable rock and impervious or impermeable rock. So water can get into here, but it can't move through here. So we have water entering this unit trapped between two right here. Whoops. Okay, and it stays contained within here, but it's under enough pressure. If you have water within this confined layer is up to this elevation. If we drilled straight through it, all the water within there wants to reach the same elevation, right? Fluid wants to fill its entire space and it wants to be level. So what happens is if you puncture a hole in that water is going to flow up because it wants to keep trying to reach that equal level to the rest of the water, which is when you get an artesian well. Artesian wells result from an inclined aquifer. So you get an aquifer that has a slope to it that transports water downslope into a region where you get the upslope section, the water has a higher elevation than in the downslope. So when you drill a well into the downslope, it wants to reach the same elevation as your upslope. You can see by this light blue line here. Okay, that's your pressure surface. Your well wants to reach that pressure surface. I'm not going to test you on this. So don't worry if you're kind of struggling with this. This is something I get into more in a 400 level hydrogeology class. When you put a well into your ground, you actually pump down the groundwater. This pumping can cause what's called a drawdown of the water table, and it causes a cone of depression in the water table. Now, most of these cones of depression for domestic uses are very temporary, and they recharge fairly quickly once you turn the pump off. So most homes don't have to worry about drawing down the water so much that you dry or dewater your well. However, if you have a residential well and then a field well, and you put in a high capacity well for industrial or construction activities, it is located lower than the other two wells, and it pumps at a much higher rate. Well, because of this, it pulls down a much larger, much deeper cone of depression, dewatering the other two wells. Now, all of a sudden, these wells can't reach the water table because this one is pumping so much water so continuously that it is significantly lower the elevation. It's important to note that while water is never created or destroyed in our system, groundwater is not renewable. Okay, water tables reflect the balance of recharge and removal. If you have increased withdrawal in a drought, you get a long-term drop in the water table. Additionally, if you have an increase in demand, you have a groundwater depletion. Out west, they're having significant issues with increased demand because of population and drought conditions, increasing the need for groundwater systems, and they're overpumping their systems to the point where the groundwater recharge can actually not keep up, and they're dewatering their aquifers. Additionally, groundwater withdrawal can cause what's called land subsidence. When water is pumped out faster than it can be replenished, as it's removed, that weight of the overburden is transferred into the sediment. So that water had been supporting the overburden. Well, the water's not there anymore. It's all empty void space. And now that overburden collapses. This is a good example of it in San Juan Valley, I think. 1925, it was about 9 meters. Land surface was about 9 meters higher than it is today. Additionally, we run into problems of contamination. Sources of groundwater contaminant include industry, sewer systems, and farm waste. Some of these can be purified just through the nature of the aquifer. As water moves through soil or rock, those soil particles will actually filter out some contaminants, but you can get a lot of contaminants that do make it into the groundwater. Old city dumps that didn't have clay liners, creating an impervious barrier, or a significant problem with polluting city waters and private water supplies for a long time. Groundwater also has a geologic impact. It is typically mildly acidic and contains weak carbonic acid. This carbonic acid interacts with limestone and dissolves the calcite within the limestone, eroding and weakening those rocks. This creates what is known as karst topography. Karst topography is formed when limestone is dissolved near the Earth's surface, typically found in an area with very poor surface drainage. It commonly creates what are called sinkholes. These are surface depressions formed when the acidic water dissolves bedrock. So you get the bedrock dissolving, and it loses those supports, and the overlying, the overburden, the material above it, collapses down inside itself, creating a sinkhole. You can also get caves and caverns. I think the Mammoth Caves out in Kentucky are formed by the dissolution of the calcite within limestone units. Many cave systems in the U.S. are limestone system. Penn's Cave in Pennsylvania is a limestone system where the water has actually eroded enough of the bedrock that you can take a raft through it. This just shows you the progression of karst topography. So you start out with your stream in a very high water table, and then as that stream starts to erode down, you see you have a drop-in water table. Well, the water had been filling these sinkholes here. These sinkholes have now become dry. And as the water starts to dissolve the limestone around it, it starts to make these larger and larger caverns that are filled with water. As you start eroding down to sea level, as the stream continues through time, you dewater these caverns, which then, if they're close enough to the surface, actually start collapsing in on themselves. Here's an image of a sinkhole. I wish I remember where this one was. It might be in your textbook. This is a very large scale. They're typically not this big, although there are some out in Washington State that are giving them some issues right now. Here's someone built their house on a sinkhole. And caves are formed by dissolving rock below the surface. Common cave features are stalactites, which are formed hanging from the ceiling, and stalagmites, which grow from the floor. And there's just some cavern pictures. So how to tell them apart is stalactites hold tight to the ceiling, and stalagmites might grow all the way up to a stalactite. Very exciting. Okay, that is the end of this week's lecture. You have your Mastering Geology assignment. Please remember to do that. You have your discussion board. There is no additional lab or any other assignment, so you should just have those two things this week. If you think you are missing anything, if you had issues submitting your rock assignment, contact me, let me know. I think most people have gotten in touch with me about that now. Your first exam is coming up in about 4 weeks, so I want you to be ready for that. If you have any questions or need any additional help on any of the material, please let me know. I would be more than happy to explain anything you might not have understood or give you some additional resources to kind of help you better understand the topic that you might be struggling with. I can also point you to what are called like study areas on your Mastering Geology website that can help out. And I think that is it. So I hope you all have a good evening, day, whenever you watch this video.